Well, I guess I will go ahead and start. Getting steadily closer to my goal of lecturing to an empty classroom one of these days. Maybe I'll manage to do it at least once before the end of the semester. But we're grading homework 2 tonight, just as an FYI. You can watch for it on Sakai. If you turned it in and you don't see a graded homework 2 on Sakai, then send us an email and I'll try to figure out what's going on. In any event, today is the last lecture on bootstrapping. Hopefully it hasn't been too horribly confusing. Today's lecture is bad once again, I apologize, but like I said, there will only be simple examples on the homework and it won't be heavily emphasized after that. As I said, this is mainly just a statistical literacy thing. I just want you to know that these methods exist. So that if you ever need to report a confidence interval for a median, you know that it can be done, sort of thing. So today we're going to be discussing hypothesis testing using bootstrapping. On Friday we discussed how you can use bootstrapping to calculate confidence intervals for whatever statistic of interest you have, even if you don't know the sampling distribution of that particular statistic. And not surprisingly, if you can calculate confidence intervals, you can perform hypothesis testing as well. But it turns out that this is harder than calculating confidence intervals for a variety of reasons. And my personal opinion is I'm not sure whether it's worth the bother of doing it at all, as I will describe today, but just in case you ever need to do it, I'll give a brief overview of how it can be done today. So, why is hypothesis testing using bootstrapping a pain? Well, in general, when you perform hypothesis testing, you assume that your null hypothesis is true, you calculate some sort of test statistic that has a known distribution under the null hypothesis, then you compute the probability of observing a test statistic as extreme or more extreme than the test statistic you observed under the assumption the null hypothesis is true. If you get a test statistic that's too extreme, you assume that your null hypothesis must be false. Easy enough. Well, in general, to do hypothesis testing using bootstrapping, you need to resample the data under the assumption the null hypothesis is true. And in general, there's not necessarily an easy way to do that. So, I'll give a few examples today showing why this can be a pain, but in general, it's resampling under the assumption this null hypothesis is true. There's no general approach to do it. You have to kind of do it on a case-by-case basis. And I mean, another problem is that p-values are approximate and sometimes very approximate. And I mean, granted, the same thing's true for confidence intervals, but it tends to be less of a problem for confidence intervals in that confidence intervals by definition are probabilistic. If you create 195% confidence intervals, then on average 95% of them should contain the true mean. So if you use something like bootstrapping where the confidence interval can vary from run to run, that's not a huge deal. P-values, on the other hand, people have this religious faith in this cutoff of 0.05. So if there's a method that gives you a p-value of 0.03 one time and 0.07 the next time, that will cause a lot of people to panic, even though for practical purposes there's very little difference between the two p-values. I mean, the final problem with bootstrap-based hypothesis testing is, as I've complained about repeatedly in this course, that people tend to overinterpret p-values, that they treat 0.05 as an almost mystical cutoff, assume that anything that's less than p is less than 0.05 is a true result that will be infinitely reproducible till the end of time, but you get p equals 0.06, it's a non-significant result and can completely be ignored as a failed experiment. It's really kind of absurd, but for this reason, I always say that confidence intervals get underused and statistics and p-values get overused, but so that leads to like the first possible way to do hypothesis testing. With bootstrapping, the first option is just don't even calculate the stupid p-value. Just use the fact that there's a correspondence between p-values and confidence intervals. To use bootstrapping to calculate a 95% confidence interval for your test statistic, if the hypothesized value of the test statistic is outside the 95% confidence interval, then reject your null hypothesis. And if you want to say that your p-value is smaller than just p less than 0.05, you can calculate 99% confidence intervals or 99.9% confidence intervals or whatever, and then you say that implies p less than 0.001 or whatever the case may be. And for the record, if you haven't figured this out from just listening to my rant about my dislike of p-values, for the purposes of the homeworks in this class, if you take the option of not reporting p-values at all, I am completely happy with that. So, when I ask you to do hypothesis testing based on Bootstrap, if you just want to calculate the confidence interval, say null hypothesis outside the 95% confidence interval, reject, works for me. And advantages and disadvantages of this approach. Advantages, like I say, it is easy. Well, at least as far as anything that involves bootstrapping can be said to be easy. If you're already calculating the confidence intervals, you've got the confidence intervals, you don't need to mess around with doing the hypothesis testing. As I said, my personal opinion, confidence intervals tend to be more informative than p-values anyway. So it saves you work and it gives you a more informative number. What's not to love? Well, the main drawback to this approach is that if you try to write a paper containing only confidence intervals and no p-values, that's the sort of thing that can make reviewers angry, and they may say, we are not accepting your paper unless you report p-values. Kind of dumb in my opinion, but such is the world. So if a reviewer insists on reporting p-values and calculating hypothesis test about some statistic using bootstrapping is important to your paper, there's other ways to do this that I'll discuss today. Another way that you can test hypotheses using bootstrapping is with permutation tests, and these are used fairly commonly in real life if you're just trying to test the null hypothesis that two means or two medians or two other measures of central tendency are equal. And the idea is that if you have two data sets and you want to test the null hypothesis, they have the same distribution, then, once again, I lost my bars in Keynote. This should be then x bar minus y bar should be close to 0. But how do you decide how close to 0 is close enough to 0? So, what if you combine both the x's and the y's into one long vector, and to calculate x bar minus y bar, you can do the following. You take the mean of the first m elements, i.e. x1, x2 up to xm, and then take the mean of the final n elements, i.e. y up to yn, and then you subtract the mean of the final n elements from the mean of the first m elements to get x bar minus y bar in general. Now, if the null hypothesis is true, then the x's and the y's should have the same distribution. And if that's the case, if you take the original vector with all the x's at the beginning and all the y's at the end and just randomly permute it, it should have the same distribution as the original x bar minus y bar. Now, of course, if like the x's have a larger mean than the y's, then this x bar star minus y bar star should have a different distribution than x bar minus y bar. So you can use this fact to test the null hypothesis that the distribution of the two groups is the same. Recall permutations. I think I've discussed this at some point, and you may have seen this outside of class, but the basic idea behind a permutation is you keep the same numbers, but you just scramble the order. So this slide shows an example of a couple of permutations of the numbers 1 through 10. In R, if you just say sample 1 colon 10 without telling it to do it with replacement, then by default it will give you a sample of size 10 without replacement. In other words, it'll just permute the numbers, scramble their order. So you see the numbers 1 through 10 in random order here. I repeat the command 5 times. Each time I get the numbers 1 through 10 in a different random order. Oh, how can you perform hypothesis tests using permutation tests? Well, first of all, you calculate x bar minus y bar for the original data. Then you combine the vector. You combine the x's and the y's into one long vector and then randomly permute it. Then take x bar star minus y bar star, where x bar star is the mean of the first m elements and y bar star is the mean of the final m elements. And so then you get a difference x bar star minus y bar star. You repeat this process b times. B is typically around 1,000. And then to approximate your p-value, you just calculate how many times the x bar star minus y bar star is bigger than the original x bar minus y bar, divide it by the number of permutations. The idea is that if the null hypothesis is true, then x bar star minus y bar star should have approximately the same distribution as x bar minus y bar, and this count won't be particularly large. On the other hand, if, say, the mean of x is bigger than the mean of y, then x bar minus y bar will be larger than x bar star minus y bar star. This count will be small, and you'll get a small p-value. So, just as an example of permutation testing in R, we'll use the plant growth data. I think we also used this for 2 sample t-tests way back when, that, as you'll recall, in this particular experiment there's a control group and 2 treatment groups. We want to test the null hypothesis that the average growth of the plants is the same in all 3 groups versus the alternative hypothesis that some of the groups experience different growth levels than the other groups. As you'll recall, I think when we did this with ordinary 2 sample t-tests, we found that treatment 2 seemed to result in significantly higher growth than either of the other 2 groups, and the 2 other groups didn't differ significantly from one another. So, how do you do permutation tests in R? Well, first of all, I'll define an R function to perform the permutation test, sort of like we define the R functions to do bootstrapping on Friday. That once again we define a function that takes 2 arguments, namely x and I, where x is a vector of data and I is a vector of indices. And first we randomly permute the x's, then we take the mean of the first 10 x's minus the mean of the final 10 x's and return that value. And then we can do the bootstrap calculations in R. It's a similar syntax to what we've done before. We use the boot function in R again. C, go boot, in the input vector I just use the C function to concatenate the weights for control and treatment 1 and control and treatment 2 and control. Note that I did it in different orders because in order for the function to work, the group with the larger mean has to be first in the vector. So, as you'll recall from the box plots, the control group had a higher mean than treatment 2, but the treatment 2 group had a higher mean than the control group. So in the first permutation test, I put control before treatment 1. Second permutation test, I put treatment 2 before control. So, and then I give it the bootstrap function that I define, mean.ptest, and say I want 1,000 bootstrap replications. Then I add this final parameter they haven't seen before where I say sim equals permutation. When you add that sim equals permutation parameter, that tells R that you want to do a permutation test. As you'll recall, under regular bootstrapping, R will resample from the data with replacement. When you do a permutation test, you're permuting the data, i.e. you're resampling the data without replacement. Hence you have to say sim equals permutation to tell it that you want to resample without replacement in this case. So, in general, if you say boot x boot.stat b sim equals permutation, that will perform a permutation test in R. And as I said, rather than resampling with replacement from the data vector x, this will tell R to resample without replacement, that is, to permute the data. And now to calculate the p-values for the permutation test, we just count the number of times that the permutation test statistic x bar star minus y bar star is greater than the original x bar minus y bar. The way you can do it in R is with this syntax here. As you'll recall, plant growth.ptest.cv1 and plant growth.ptest.cv2 were outputs from the boot function in R. And the output of the boot function in R, if you say $T0, that will give you the value of the bootstrap test statistic for the original data, in this case the unpermuted data. And if you say output of the boot function $T, that will give you a vector of length 1000 or length however many bootstrap replicates you have, or each element of that particular vector is a value of the bootstrap test statistic. So what this R code is saying is count the number of times that the bootstrap test statistic, in this case the permutation test statistic, is greater than the mean differences for the unpermuted data, divide by 1,000, then multiply by 2, so we want a two-sided test. We get a p-value of 0.256 for testing the null hypothesis of no mean difference between control and treatment 1. We get a p-value of 0.04 for testing the null hypothesis of no mean difference between treatment 2 and controls. And as I said before, in general in R, if you save the output of the boot command, call it boot.object, it will have the following data sets. Boot.object $T will be a vector of length b, usually a vector of length 1000, containing the bootstrapped values of the test statistic, in this case the permuted values of the test statistic. Boot.object $T0, that will give you the test statistic for the unpermuted data. They'll just be 1 because there's only one unpermuted data set. And in general in R, if you say sum x greater than y, that'll give the number of times the vector x is greater than y. So when you say sum boot object $t greater than boot object $t0, it says how many times is your bootstrap test statistic more extreme than your original test statistic. And if you remember p-values from several lectures ago, which I'm sure you don't, is why I calculated them again, if we do a standard t-test, we get p-values that are very close to what we get from the permutation test, that for testing the null hypothesis of node mean difference between controls and treatment 1, we get a p-value of about 0.25. For comparing controls to treatment 2, we get a p-value of about 0.05, slightly less, nearly identical to the bootstrap, or the permutation test p-values in this case, which is reassuring that hopefully the permutation test does seem to be giving reasonable results. And another way that you can calculate p-values for using bootstrapping is to base your p-values on bootstrap confidence intervals. We discussed this briefly on Monday, that given a confidence interval with coverage probability 1 minus alpha, then, well, I guess maybe I should phrase this differently. Let's say we use Bootstrap and we get some test statistic, or I mean, we don't even have to use Bootstrap and get a test. Let's say we have some test statistic. Let's say we find a confidence interval such that this test statistic is on one end of the confidence interval, either the upper end or the lower end, doesn't really matter. And we'll say that the confidence interval such that the observed test statistic is on one end of the confidence interval has coverage 1 minus alpha. Then you can show that the p-value for testing the null hypothesis that the test statistic is equal to the hypothesized value will have a p-value of alpha. You can, if that's not obvious, you can think it through, or you can just take my word for it. But the point is that if we want to calculate a p-value to perform hypothesis testing using bootstrapping, we can as you can tell, I didn't sleep enough last night. You can find a bootstrap confidence interval such that the bootstrap test statistic lies on one end of the confidence interval, then calculate the coverage level for that confidence interval, and use that to calculate a p-value. So what that means for practical purposes, if you want to test the null hypothesis, the difference between two means is 0, you can just count the number of times the bootstrap differences means is less than 0, multiply by 2 if you want a two-sided test, divide by the number of bootstrap replicas. So in R, the way you can do this is, rather than doing permutation tests, you just do stratified bootstrapping, where I'll use my same mean.ptest function again, where basically I take the mean of the first 10 elements minus the mean of the final 10 elements, and I'll do the same thing where I combine the control weights and the treatment weights into one vector, or combine the treatment 2 weights and the control weights into one vector. This time, rather than doing a permutation test by saying sim equals permutation, then I'll just do stratified bootstrapping, where I say resample from the controls, resample from the treatment groups, and then calculate the difference x bar minus y bar under the bootstrap after resampling from both the x's and the y separately, calculate that difference, and then just count the number of times that difference is less than 0, and multiply by 2 and divide by 1,000. Once again, we get p-values about 0.24 and 0.03, very close to what we got using either t-tests or using permutation tests. Suggesting this approach also gives us reasonable p-values for testing the null hypothesis of no mean difference between these groups. So, is there some reason to prefer permutation tests versus bootstrap-based tests? Well, one thing to keep in mind is that permutation tests don't actually test exactly the same null hypothesis as a bootstrap-based hypothesis test. Permutation tests will test the null hypothesis that two distributions are the same, versus bootstrap-based tests will test the null hypothesis the difference in means is 0. So if you're really interested in the null hypothesis that the difference in means is 0, then the null hypothesis for permutation tests may be too stringent. For example, what if the means are different but the variances are the same? If you look hard enough, you may be able to construct some convoluted example where two data sets have the same mean but drastically different variances, so when you use the permutation test, you get a significant result even though the difference in means is negligible. In practice, this usually doesn't happen unless you go out of your way to find a really convoluted example to try to break it. It's usually, people quite regularly just use a permutation test to test the null hypothesis. The means of two groups are the same without even worrying about this, so it's probably not a major deal. But it is something to keep in mind. And in practice, they usually give very similar results. One nice thing about the bootstrap approach is that it gives you, the bootstrap approach will give you a confidence interval for the difference in means, whereas in general that's hard to get from permutation tests. That's one reason to prefer the bootstrap approach. Just because, like I say, anytime you can report a confidence interval, you should. One possible reason to perform permutation tests, and perhaps the most popular area where permutation tests are used nowadays, is if you're analyzing high-dimensional genetic data. In particular, if you ever work with microarrays at all and use like the significance analysis of microarrays, i.e. SAM software, basically it uses permutation tests to test the null hypothesis of no differential expression for each gene. And there's a couple reasons why the SAM software does this. First of all, it's not unusual to have very small sample sizes in gene expression data. And as I said, bootstrapping and permutation tests work even if the assumptions of the t-test are violated. And even though the t-test tends to work remarkably well, even if your assumptions are in fact violated, if you're doing a gene expression experiment with like 30,000 genes on it, inevitably for some of the genes the assumptions are going to be violated so badly that the t-test is going to be invalid. Well, maybe if you have a large enough data set it won't be an issue, but if you're comparing like 5 cases versus 5 controls, which happens sometimes in microarray experiments, you're looking at 30,000 genes, you wouldn't want to assume that the t-test works for each one. So why do they do permutation tests rather than bootstrapping? Well, purely computational reasons. If you did bootstrapping, that requires you to resample from your original data with replacement, so you have to make a copy of this huge microarray data set with 30,000 rows, in memory and then manipulate that data set, which I mean with modern computers isn't the end of the world, but it's going to slow you down. If you do permutation tests, all you have to do is permute your case control labels and then recalculate the means. You only need to keep one copy of this huge data set in memory. So from the perspective of a bench scientist, at least in my experience, that's the most common place where you will see permutation tests used when you're analyzing the output of high throughput genetics experiments, because permutation tests work quite nicely in that situation for a variety of reasons. And as an aside, I'll talk about this a bit more later. Sometimes in papers and so forth, you'll hear about like Wilcoxon tests and things like that. A Wilcoxon test is an older version of a test for testing the null hypothesis that two means are equal to one another in cases where you don't believe that the assumptions of the t-test are satisfied. My personal opinion is there's no reason to use it anymore because bootstrap tests and permutation tests will do the same thing, and typically they'll give you better power than something like a Wilcoxon test. But so I'm not really even going to bother to teach those at all, but just in case you ever see one, it's used for the same thing as permutation tests and bootstrap-based hypothesis tests. Well, anyway, now I'm briefly going to discuss ways to improve bootstrap estimates of p-values. This is kind of, I debated about whether to really put this in the lecture at all, and if I ever figure out something more useful to put in the second half of this lecture, I will. But because I'm definitely never going to ask you to do this, my personal opinion is that in almost all situations, what I'm about to say is a bigger headache than it's worth, and hence probably not worth using. So why are you even listening to this? Good question. If you want to go so that I can like fulfill my goal of lecturing to an empty room, go for it. But just in case you're rapidly curious, there are ways you can get better bootstrap estimates of p-values, because the bootstrap estimates of p-values we discussed previously usually give you good results, but they're not necessarily 100% accurate. And without boring you too much with the details, the reason that you can sometimes get wonky estimates is that not all of your bootstrap samples will necessarily have the same variance. In the vast majority of practical situations, the variance won't change that much from sample to sample. So if you just use the permutation test / bootstrap tests I've described thus far, you'll be fine. But if the variance varies quite a bit from sample to sample, you can find situations where this will give you weird results. So you can get better bootstrap estimates of p-values by taking random variance into account. So let's say we go back to our loblolly pines example. We want to do a one-sample hypothesis test the null hypothesis. The mean height of the pine trees is 30. And we've shown previously that if the null hypothesis is true, then the test statistic sample mean minus the hypothesized mean divided by the sample standard deviation over root n, that will not depend on the unknown value of the variance. So if we bootstrap this particular test statistic, rather than just taking the sample mean minus 30, then you can avoid this problem that can arise if the variance varies too much from sample to sample. So here's an improved way to calculate bootstrap p-values, that basically you calculate your test statistic, in this case we call it t for the original data, then you resample the data under the assumption that your null hypothesis is true, count how many times that the bootstrap test statistic is larger than your original test statistic. Divide that by the number of bootstrap replicates to get your approximate p-values. So how that requires us to resample the data under the assumption that the null hypothesis is true. How exactly can you do that? Well, if the null hypothesis is true, then x bar should be equal to 30. So we basically transform the data x to a set of variables z, where you take each element of the data set, subtract x bar, add 30, and then you resample these zi's. Because if the null hypothesis is true, then the distribution of these z's should be the same as the distribution of the original axis. So here's some code to do this in R. Like I said, this is definitely not something I'm ever going to ask you to do in this class. If you want to do it so that you can impress us and make us think that you're smart when we grade the homework, go for it, but you certainly don't need to. Basically, I define my bootstrap function in the usual way, where take data x, a set of indices y, let x stars be x of I, and then the value it returns is just a t-statistic where I take the mean of the permuted data minus 30, or the mean of the bootstrap data minus 30 divided by the standard deviation divided by the square root of n, and then return that. And then to implement this in R, I first calculate the test statistic for the non-bootstrap data, take the mean of height minus 30 divided by the standard error, standard t-statistic. Then I convert the height to this height.z variable, where I take the height minus the mean of the height plus 30. Then I bootstrap this height.z variable past my mean.p.boot function with 1,000 replicates. Then I count the number of times that this bootstrap test statistic is greater than my original test statistic, divide by the number of replicates, multiply by 2 for a two-sided test. Voila. Get a p-value of about 0.3. And if you go look at the old slide, that's pretty close to the p-values that I got earlier. And now if we want to do this in the two-sample case, you'll recall from the two-sample t-test that if the means of x bar and y bar, or not x bar and y bar, it's actually r x and y, the means of x and y are equal, then the distribution of x bar minus y bar divided by the pooled standard error has a t-distribution that's independent of the unknown variances. So you can calculate t from this test statistic t from the original data, and then resample under the assumption that the means are equal, and see how many times in your resampled data set you get more extreme test statistics than with your original data. So how do you resample under the assumption that the means are equal in this case? Well, if you can take the combined sample again and let W bar be the mean of the combined sample, then you define variables V and Z to be equal to take each x, subtract the mean of x, and then add the overall mean. Likewise for the y, subtract the mean of y, add the overall mean. And if the null hypothesis is true, then the distribution of the t-statistic applied to these v's and z's should be the same as the distribution of the t-statistic on the original data. So we can compute t star by resampling separately from the v's and the z's. So here's the command to do us in R, and I'll apologize in advance for the fact that it's so convoluted, but we define a bootstrap function again. Take the mean of the first 10 minus the mean of the final 10 divided by the pooled standard error. Then take the control weight, the treatment 2 weight, and then calculate the test statistic for the original data, then convert the control and treatment weight to the z variables by subtracting off the mean of each group and adding the overall mean, then feeding all of that into a big stratified bootstrap thing, counting the number of times you get a test statistic more extreme than the original test statistic divided by 1,000 multiplied by 2. Oh. And in practice, unless you're looking for really precise p-values, I think this is a much bigger headache than it's worth. Implementing it is not fun, if you couldn't tell that from the previous slides. And generally speaking, the improvement in accuracy usually is not good. And unless you set b to be a very large number, it's unlikely that you'll get more signal than noise. In fact, in this case, it looks like the p-value was actually further away from what it theoretically should be than if we hadn't bothered with any of this. One case where you may want to consider it is if the variance of your bootstrap replicates varies drastically from replicate to replicate, and you're trying to publish in the New England Journal of Medicine or something like that, and you need a very precise p-value estimate, then maybe you do something like this just to make it absolutely bulletproof for reviewers. Otherwise, I don't think it's worth the trouble. And another issue with all of this is that for this method to even work, then you have to have a test statistic that's independent of any unknown parameters. Well, if you have a test statistic that's independent of any unknown parameters, that begs the question of why the heck are you bootstrapping in the first place? Just use a t-test in that case. So, I mean, I suppose that same sort of thing applies if you had a really small sample and you're worried that the assumptions of your t-test aren't satisfied, then maybe this is something to worry about, but rarely is that much of a problem in practice. And if you wanted to do something like test null hypothesis about the difference in medians, for instance, to apply this method, you would have to come up with an estimate of the variance of the difference of the medians. There actually are ways to do that, but you really want to bother for something that doesn't improve the accuracy that much. I mean, in practice, I've never actually used this method. I mean, I try to avoid calculating p-values for bootstrap test statistics in general, and when I do, I mean, I just use some of the more brain-dead approaches, but tossing this out there in case it ever needs to be done. And as I said before, this mentioned in passing the existence of non-parametric hypothesis tests, that once upon a time, before we had bootstrapping, if you wanted to compare the null hypothesis, if you wanted to test the null hypothesis, the mean of x is equal to the mean of y, but you didn't think that the assumptions of the t-test were satisfied, you could use these non-parametric tests like the Wilcoxon test, the Kruskal-Wallis test, and things like that. And I mean, a large number of elementary statistics courses throughout the country still teach these tests, and you'll still see them used in papers and so forth. And in my opinion, there's really no reason to use these anymore now that bootstrapping exists and is easy to calculate. It's like a bootstrap-based t-test versus the Wilcoxon test. Other things being equal, the bootstrap-based t-test will give you better power. So the Wilcoxon test to me is somewhat anachronistic these days, but I'll mention this exists just so if you see it in a paper, you know what the heck they're talking about. It still gets used just because it gets taught in elementary statistics classes and bootstrapping doesn't, so people use what they're familiar with. I'm teaching bootstrapping to you instead of the Wilcoxon test in hopes that someday, 30 years from now, these other non-parametric tests will be given their proper burial. So, some final comments on pros and cons of these various approaches. Permutation tests, you do see them used a fair amount nowadays when the assumptions of the t-test are violated. They're becoming an increasingly popular alternative to things like the Wilcoxon test, particularly, as I said, in high throughput genomics. They offer certain computational advantages. And drawbacks to permutation tests, they can only be used for two sample problems. You can't use a permutation test to test the null hypothesis the mean is equal to 30 or whatever. And they also require you to assume that the two distributions are identical under the null hypothesis, not just assume that the means are equal, which is a weaker assumption. In practice, that usually doesn't matter. If you look hard enough, you can find some cases where means are the same, but the permutation test still tells you that the distributions are different. And in principle, any test statistic can be used for a permutation test, because like I said, the permutation tests are testing the null hypothesis that the distributions are the same, not that the means are equal. So any sort of statistic that would be different, if the distributions are different, you can use for a permutation test. So it could be mean, median, interquartile range, ratio of variances, whatever strange thing you can come up with. In practice, you're almost always want to test the null hypothesis that a certain test statistic, usually a measure of central tendency, either mean or median, is the same as in the two populations, so you use that as your test statistic. And these other bootstrap-based hypothesis tests, you won't see them very often, partly because very few people know about them, and partly because they're non-intuitive and kind of a pain to code. And when you use them, they're usually just to give you a rough estimate of p-values that there would otherwise be no way to calculate, like a p-value for testing a null hypothesis, the median of two samples is the same or something like that. And the advantages of bootstrapping as opposed to permutation tests is it'll give you confidence intervals, and in fact you can use bootstrapping to get confidence intervals for permutation tests, although I won't go into that. So things to remember for today: we can use permutation tests, test the null hypothesis, the two samples have the same distribution. You can also get approximate p-values and confidence intervals for test statistic using bootstrapping. And you can increase the accuracy of bootstrap confidence intervals if you find a test statistic that doesn't depend on unknown parameters, although it's usually a bigger headache than it's worth. And here's the one new R command today, that if you use the boot function with sim equals permutation, then you can do a permutation test. Any questions about any of this stuff? We're done with bootstrapping after today. The rest of the class should be easier. So if these last couple lectures were a little crazy, it's downhill from here, hopefully. Okay.